that worked well in our textbook that I want to add on in 3.4. And then I want to start a little bit of 3.5. That's going to finish us for today. Plan for next class will be, I'm going to give you guys this handout here at the end. You have all of next class to work on it. It's just derivatives practice using chain product quotient and then the rules that you've seen to this point. Lucia?
So we have 3.4 homework.
Yes. That'll be the only homework set due this week. Yes. So I'm on the 3.4 tab right now, but I'm just going to be there for like one little topic, and then we're going to jump to the bonus 3.4. We'll be there for a minute, and then go to 3.5. So we'll be in 3 different tabs today, which is not perfect, but like answer your question, I hope, right? All right. So the one thing that I didn't talk about that I think in enough detail was this new additional derivative rule. So this is what I want to start with today. So this rule says the derivative of a to the x is equal to a to the x times the natural log of x. So this is a new derivative rule. Should this be memorized? Yes, it should go on with the rest of your memorization list. Just to make sure, we already have a derivative rule for e to the x. Let's just make sure that this rule still satisfies e to the x, right? This is like a more general version. Yep. So if I follow that new derivative shortcut I've just been told, the derivative of e to the x should be e to the x times the natural log of e. What's the natural log of e? 1. 1. So this is still e to the x, which is what we should get. Everybody agree? So this new rule seems to cover that old rule, which is what we want. It's a generalization. So to prove this, what I'm going to start by doing is I want to rewrite a as some power of e. Since I know how to do the derivative of e to the x, how can I rewrite a as a power of e?
Log. Yeah, log base e of a.
Yeah, and log base e is just the natural log, right? So that works perfectly. Everybody feel good there? So then a to the x, well, that can just be e to the ln of a to the x, right? Everybody feel good?
Oh, that's natural log.
Everybody feel okay there? Mm-hmm. And then when I have an exponent of an exponent like that, how do I simplify that? Multiply. Mm-hmm. So we'll just write this as e to the natural log of a times x. Everybody feel good there? So I have then the derivative of a to the x is just the derivative of e to the natural log a times x. Feel good so far? When I look at the derivative of e to the natural log a times x, what do you notice there? How would I do that derivative? Yeah, chain rule. Very good. That's a composition, right? The outer function is e to the x, and the inner function is natural log a times x, right? So if I apply the chain rule, I have that. Everybody feel good so far? What's the derivative of natural log A times x? You don't need a product rule for that. Why not? I have two things multiplied together. Is A a variable? No, it's a constant, right? So the derivative of natural log A times x is natural log A. Yeah. And that's exactly what we wanted to end up with. Right, that was the statement that we started with, that we're trying to prove. Does everybody feel good?
Mm-hmm.
So again, new derivative, shortcut to add to your list of things to memorize. Oh, Mr. Kulik, are we almost done? We're getting close.
And then
Well, we have inverse trig still to talk about and logs, and then we'll be done. But there's no more big rules. The inverse trigs are nasty though. We thought the trigs were confusing looking. For Bob Brooks.
So what is this one telling us? Like,
Just how to take the derivative of like 2 to the x.
okay.
That's all it's doing. Just telling us how to do that. So the
Oh.
derivative of 2 to the x is 2 to the x times the natural log of 2. That's all it's telling us. Does that feel okay?
Yeah.
So it just allows me like some more variety and like packing together more derivative rules to put on your test, right? And now I can take this derivative rule and use it like in conjunction with chains or products or quotients. Oops. All right. What's that?
No,
It's just like, you know. That's all it's saying, right? Just telling you how to do stuff like, you know, some constant to the x, 10 to the x, 13 to the x.
Okay, that makes more sense.
And then I can use that in conjunction with like a product rule. If I had 2 to the x times cosine x, it just becomes like part of a product rule or part of a quotient rule or part of a chain rule or whatever, right? Just like sine, the derivative of sine can be part of a product rule or a quotient rule or a chain. You guys get what I'm saying? Is that okay, Brooks?
Yeah.
So the section that's like our bonus 3-4 content that our textbook I don't think does a particularly good job of hitting on, but is a common AP topic, is this idea of, you know, taking the derivative of inverse functions. So when you're told two functions are inverses, these are the two like algebraic statements you get. Right? We know that f composed g of x equals g composed f of x, which is all equal to x. Right? That was our definition of an inverse. You remember that from pre-calculus and algebra 2? Furthermore, that if f and g are inverses and f takes a to b, then g should send b back to a, right? So if f of a is equal to b, then g of b is equal to a. You guys okay with that notion?
Mm-hmm.
All right. So what we're interested now are derivatives that involve an inverse. So if we have this, right, f and g are inverses. We can say this. I can take the derivative of both sides of this equation, and just like in algebra, if I do something to both sides of the equation, equality is maintained, right? So the derivative of f of g of x is going to require the use of the chain rule. So that's just going to be f prime of g of x times g prime of x. And the derivative of x is 1. So if I then divide both sides by f prime of g of x, I have that. Everybody okay with that idea? When is this true? Only if f and g are inverses. Is everybody okay?
Will we be told that they're inverses, or will we?
Well, let's look at some example problems right after this, and you'll see exactly how things are going to be phrased. But that's exactly the right question, right? So we're told functions f and g are differentiable. As soon as I hear the word differentiable, what else do I know is also true about f and g? Continuous. Now, I don't know if that's going to be important or not, but as I'm reading a question, whenever I hear differentiable, I think also continuous. So just kind of like trying to describe my mental process as we're going so you can help see what I'm seeing when I read a question. It says for all x, f of g of x is equal to x. What's that mean? F and g are inverses, right? We were just told it algebraically instead of in words.
Okay.
Is that okay?
How do you know that means that they're inverses? Okay.
One of our definitions of inverse, right? So as soon as we see inverse, we get these two things for free. And in fact, that's like an if and only if statement. Okay? And we got both directions, right? We need both directions. Okay. So it says if f of 3 is equal to 8 and f prime of 3 is equal to 9, what are the values of g of 8 and g prime of 8? So what does f of 3 equal to 8 also give me, since I'm dealing with inverses? G of 8 is equal to 3. Is everybody okay with that? Checked one box off. Everybody's good? You got it basically for free, right? Just had to remember that was true. And now it's asking me for g prime of 8. To do that, I'm going to use this formula. Well, it's going to be 1 over f prime of 3, because g of 8 is equal to 3, and f prime of 3 is 9, and there's my answer. Lucille.
So when I was looking at that and I was trying to solve it by myself, I would have done f prime, which is because I thought f prime was 3, and so I put 3 into f prime, and then g of 8 is also 3, so then I multiplied them together.
Right, they're not being multiplied together, right? There's a decomposition. Is that okay? Feel okay on the first one? Again, it's not difficult if you know what you're looking at. No, that's not what I wanted that thing to do at all. But if you've never seen this idea before, coming up with this on your own, that's not easy, right? Like that's not obvious, that wasn't trivial, that that's gonna be the thing that we're gonna need. So let f be the function defined by f of x equals x cubed plus x. If g is equal to f inverse of x and g of 2 is equal to 1, what is the value of g prime of 2? What's that saying? They're inverses, right? Another way of writing it algebraically. Lucy, are you okay?
How do you know that? Interesting. Alright.
So this is the notation for inverse.
The negative one.
Notice that when I read it as f inverse.
Yeah.
So if one function is equal, g is equal to f inverse, then f and g are inverses because g is f inverse.
So for this notation, you don't need them to say it both ways.
Yep, because that is included. Does that feel okay? Okay. So we have g prime of 2. Well, that's going to be 1 over f prime of g of 2, just using our formula we worked out at the beginning. And we're given g prime of, or g of 2, right? G of 2 is 1. But we don't have anything about f prime. How are we going to figure that out? Oh, yeah, we're told the function for f, right? So we'll just do f prime, which is, mean 3x squared plus 1. So f prime of 1 then is 4. So it's 1/4. It's okay? That's what, I mean.
Like, seriously.
Yeah, so part of the issue,
Really easy.
so here's the thing. And it's important to realize this. You watch me do this, right? I am a 44-year-old man who has been teaching for 18 years, 19 years, something like this. I've taught this class 4 or 5 times. I've taken 6 or 7 like continuous calculus style-ish classes in college and beyond. This is easy for me because I've done so much practice. The difference between you and me is not that I'm smarter than you, it's that I am more practiced than you. Because I've basically been doing taking the same class for 5 years. Imagine doing the same class over and over and over again for 5 years. And it depends on you driving the class every day. So like you have to know it, and you have to practice it. Like that's the difference that you see when you watch it. It's like, this looks so easy for you. It is, but not because I'm smarter than you, it's because I'm more practiced. As a high school student, I was no more capable than you guys are in this room, probably less so. I didn't take calculus in high school. You know? You guys are further along than I was as a high school student. You're better students than I was as a high school student. I didn't study one time in high school. Yeah. Never once. Just showed up and did it. Paid attention and did my homework and showed up and did it.
Did you get good grades?
It was like unweighted 3.8 or something. But like, school was easy, but I was not a good student. Like, you guys all know people like this, right? In class, that's like, this person is kind of, like, never seems like they're paying attention, but maybe they're actually paying attention. They seem to do well without really having to do much. Now, at my school, they didn't offer hard classes, right? Like, I went went to like a little tiny crummy public school or private school in the 90s that had no AP anything, and to know what an AP class was. So, just, I want to say that to be like, you know, like, all you're looking at is the result of like 20 years of practice. That's why it looks easy. And like, you know, like I'm a smart man. Like don't get me wrong, but like, you know, if you grade for, you know, like time, or like you grade for experience and practice, that's where all the difference is. Like that's where all the difference is. All right, we'll do just a couple more, and then we're gonna move on to 3.5. Sound good? And again, like this is a small little sliver of a topic. You might get like 1 or 2 multiple choice questions on an entire AP exam that cover this. But our textbook does a lousy job of it, so I wanted to make sure. And again, like the idea, not hard when you know what you're looking at, but if you see it for the first time, doubtful you come up with like how to do this. Anyway, let f and g be functions that are differentiable everywhere. If g is the inverse function of f, there it says it verbatim, right? We've seen that presented like a couple of different ways now that all mean the same thing. It's like, oh, Mr. Kula, can't they just pick like one way and do it? No, unfortunately not. That's not how mathematics works. Part of the reason is all of these things that we're learning were developed independently across like multiple different European countries, and different names and notations bubbled up in each of those different places, and nobody's willing to like discard the way they've been doing it for a century to just give it up for somebody else's, so we just use them all. Which is like, ugh. That's how it works. All right. If g of -2 is 5, f prime of 5 is -1/2, then g prime of -2 is equal to, well, g prime of -2 is going to be 1 over f prime of g of -2. And hey, we're told that g of -2 is 5. So we have 1 over f prime of 5. And hey, we're given f prime of 5. So just -2. Again, no big deal, right? If you know what you're looking at, totally doable. All right, last example, let f and g be differentiable functions such that a bunch of stuff is true. If h of x is equal to f of g of x, then h prime of 1 is equal to, now are we told anywhere in this that f and g are inverses? Either symbolically or in words. No. Can you look at this information and tell whether they're inverses or not?
Yeah, because g of 1 is equal to 2. Wait, you're gonna have what?
Yeah, not really, right? Maybe they are, maybe they are not. Guess what? Doesn't matter. So I'm going to start just by doing, I want the derivative of h at 1. I'm going to start by just computing the derivative of h. That's the derivative of f of g of x. How do I do the derivative of f of g of x? Chain rule. So derivative of the outside times the derivative of the inside. So h prime of 1 then is f prime of g of 1 times g prime of 1. Does everybody feel okay? If I go to my chart, g prime of 1 is 2. and g prime of 1 is -3. And then f prime of 2 is -4. Oops. So I get 12.
What question is it? What was on the test?
The one that we just did? No.
So you didn't have to find f prime of -3. You only found f prime of 2.
Correct. I have f prime of 2 times -3.
Okay, so you're not distributing the f prime to both, just
Correct. Because this is like its own number, and I take that number and multiply it by -3. Yes?
Let's do that.
Sure. How do you guys feel? It's all right? We're going to look at here today is the start of implicit differentiation. When we say implicit, what that means is that there's no obvious independent and dependent variables. So you can have an explicit equation like y equals 5x, where it's kind of clear that x is the independent variable and y is the dependent one, right? Everybody's okay with that? But if we write our equation where the x and y on the same side, there's no implied independent and dependent variable in that situation, right? If I have a situation where I have x squared plus y squared equals 25, there's no obvious independent or dependent variable there. Now, could you separate that to get one of the variables by itself? You could, right? That's not the best way of handling this stuff. Shall we begin? All right. Before we dive into this first example, I want to make an observation first. So let's say we just have something simple like y equals 4x. When I take the derivative of the left-hand side, what do we get? Well, when I take the derivative, what's the derivative of this? 4, right? So we'd write like y prime is equal to 4, or dy dx is equal to 4, right? Something like that. You guys agree? Now that left-hand side, when I did the derivative of y, I did a chain. You guys have been doing a chain rule there the whole time. You just didn't notice. Let me just point this out. This is really a composition of two functions. We plugged y into x. You guys will see that. Now it's a pretty silly looking composition, but that's what's really happening. So when I take the derivative of y, we get the derivative of the outside, which is 1, that's the derivative of x, times the derivative of the inside. The derivative of y, as we can write as dy dx, or y prime, either is okay. Either is okay. Me personally, I'm going to write dy dx's, because the primes are easy for me to miss. They look like to the power of 1 sometimes. It's easy for them to just kind of get lost in the shuffle, but it's fine to do that. Lucy, are you okay? Okay. You look very concerned, that's why I asked. Okay, so let's go back to this. So we want to find dy dx. So we'll start by taking the derivative of both sides of our equation. Okay? So that derivative is going to distribute across to the x squared and the y squared separately. The derivative of x squared is 2x. The derivative of y squared is 2y times dy dx. The derivative of the outside, outer function there is x squared. The inner function is y. The derivative of x squared is 2x, with the inside plugged back in. That's the 2y, times the derivative of the inside. The derivative of y is dy dx, or y prime if you prefer. So the way to remember this is if my variable that I'm differentiating with respect to differs from the variable I'm differentiating, I get one of these. Okay? So if I did, instead of doing the derivative, doing d dx of x squared plus y squared, if I did d dt x squared y squared, I'd have a dx dt at the end of the 2x and a dy dt at the end of the 2y. Does that feel okay? We're going to continue practicing this and reinforcing this in a moment. And the derivative of 25 is 0, right? Because it's a constant. Okay, if I want dy dx by itself, right, it says find dy dx. How do I get dy dx by itself? Subtract 2x and then? Divide by 2y. So, simplifies down to just negative x over y. So for part B, it says find the equation of the tangent to the circle at the point 3, 4. To write the equation of a tangent line, what do I need? Slope and a point. The point I'm given, yay! How am I going to find the slope? No. I use the derivative, right? The derivative is a slope function, right? It outputs the slope of that function at a specific point. So the slope at 3, 4 is going to be negative 3/4. Negative x over y. So far, so good. So now I can just write the equation of my line. I'm going to write my equation in point slope form because, well, I have a point and a slope, and boy, that's easy to do. You okay? And that's basically the idea there. Now notice that for this problem, I could have separated and gotten the x or y by itself, right? I could have gotten the y by itself by subtracting x squared from both sides and then square rooting both sides. What's the problem with that though? I got that nasty plus or minus floating around. I'm not really sure what to do with that. If I do the derivative of the square root of 25 minus x squared, that's a chain rule underneath there. It's gonna get pretty nasty. Eventually it'll simplify down to negative x over y, but look how easy that just fell out of there when I didn't bother trying to separate the x and y. Is that okay? Let's look at another example. Now if I look at this next one, x cubed plus y cubed equals 6xy. Well, it's not a circle because it's cubed. That's actually an elliptical curve is what we call that. Yeah, not important. Unless you're trying to understand the proof of Fermat's last theorem. It's a very famous story in mathematics. So Pierre Fermat was like a 15th century mathematician, and in the margins of one of his texts, he wrote that like a to the n plus b to the n is not equal to c to the n for all a, b, and c for n greater than 2. So it's basically the Pythagorean theorem isn't going to work. There's no solution to that equation if the power is greater than 2. And he's like, the proof of this is easy. I'll do it someplace else, but he never wrote it down anywhere that anybody could find. And nobody for 500 years was able to solve this. Like the best mathematicians of their age all took a crack at trying to solve this, trying to do this proof. It wasn't until the 1990s that a Princeton mathematician finally like did this proof, but he had to use like all sorts of modern mathematics that would have been available to Fermat at the time. And the proof is like hundreds of pages. It has like all these special cases that had to get worked through. Like it was like a major mathematics result, although like this theorem is like kind of not important, but because so many important people worked on it so often for so long and unsuccessfully, it was a really big deal when somebody was finally able to do it. And the way part of the proof is using elliptical curves. So that's where that kind of comes in. And if you're interested in like cryptography, like if you're a computer person, the way that one of the methods for encoding data over a public network is using elliptical curves to create a problem that's really difficult to solve by brute force. But it's really easy if you know the key, which is the idea behind cryptography. If you know what to do, you can undo it in a second, which is why when you click on your email, it loads instantly, even though it's encrypted as it was sent, or your text message was encrypted as it was sent, but it loads on your phone immediately. But if somebody was listening in, they're going to get the encrypted version where it's ideally takes months of parallel computing to kind of plow through the encryption to be able to read your text message from months ago. Anyway, continuing on with this, like way off topic. Wants the derivative of this. Notice here, this is not going to be separable using any method that I know of. Like no way for me to look at this and go, oh, okay, I know how to separate x and y because I have that x cubed, y cubed separate and the x, y together. Like that's not something I know how to factor right away because the cubics, it probably doesn't factor. It's probably inseparable looking at it, which is like total Bummersville. But it doesn't matter to us because we are just going to take the derivative of both sides anyways. So on the left side, the derivative of x cubed is? Yes. And the derivative of y cubed is? 3y squared dy dx, but
Why isn't there y in the top ones?
well, this is the name of the operation. This is like the result. Right? d dx is like the name of the operation, take the derivative of. The result of that is the dy dx. Does that feel okay? Yeah. It's like, like square root by itself is the name of the operation, right? I put an x under it, that's like the result of taking the square root of x. Right? d dx is the name of the operation. I put a y up there, it's the result of taking the derivative of y. Does that help kind of analogize it a little bit? I'm not sure that's not a word. All right, so get that out of there. How do I do the derivative of 6xy? What's the derivative of that? What? Yeah, who said product rule? Yeah, that's right. Where's the product rule happening? Between the x and y. Those are two separate functions, right?
d y over d to x is almost just more of like routine than actual math, right?
I'm sorry, what?
Writing d times y divided by d times x is more of like routine rather than actual like math, right?
It's more like a variable.
Yeah, okay.
Yeah.
It's a long variable.
But it's okay? Again, you can write y prime instead of this if you wanted to.
Mean the same thing?
They mean the same thing. I just write it this way because the primes are easy to kind of get lost. This, it's hard for me to lose track of.
Oh, they don't mean derivative.
Yeah. Yep. All right, everybody good with how I product ruled that? Okay, and then the derivative of y is 1
Times dy.
dy dx, yeah. So I won't bother writing the 1, I'm just going to write the dy dx. And the derivative of x is?
dy d. No, just 1.
Just 1, right? If the variable that we're differentiating matches the variable that we're differentiating with respect to, there's no extra thing.
Cool.
Everybody so far so good? Now we want to find dy dx. We have dy dx in two different places. How do I get that in one place?
Nobody knows.
Nobody knows. We all know. Yes, subtract is right. So I'm going to move the dy dx's to one side and the stuff without dy dx's to the other.
So when writing like the usual d over d dx, that usually means like the derivative. It means like you have to do the derivative, but it hasn't been done yet. But this is just like a regular variable, right? It's not implying you have to do anything.
Because when we get it by itself, you're going to see what we get. It's going to be like, oh, the derivative is this formula.
Yeah.
Okay, now what do I do? They're on the same side. Factor, yes. So the dy dx, we can treat that like a greatest common factor. And then I can just divide the 3y squared minus 6x to both sides. That's an x. Sorry. Lost that somewhere along the way.
You can't simplify that anymore?
I mean, you could reduce a 3 out, I guess.
No, I was just wondering.
Sure, do a little bit. Sure. Everybody okay? Again, so what do we have here? This is just the formula to find the derivative of this function, right? Okay. Part B says find the tangent at the point 3, 3.
So we have plugging
Yeah. So my slope is going to be 2 times 3 minus 3 squared over 3 squared minus 2 times 3.
6 minus 9, 83 over.
Mm-hmm.
So,
No big deal, right? All that derivative is just a formula to find slope. So to write a tangent line, I just plug the point into the appropriate place, simplify down, get myself a slope. All right. Part C says, at what point in the first quadrant is the tangent line horizontal?
would that be when it's pi over 4? It's like or 2 divided by 100.
Not when y equals 0.
And the slope is 0.
When the slope is 0, okay, horizontal means slope 0.
Oh, so it would just be.
And what's slope really mean for us? So dy dx equal to 0. So 2y minus x squared over y squared minus 2x is equal to 0. But there's one other condition it had in that statement, right? What was the whole statement again?
First quadrant.
First quadrant, what does that mean? Good, x is greater than 0 and y is greater than 0. Don't know where we're going to use that yet, but I'm going to write it down because I know that has to be true. There's probably going to end up with a plus or minus from a square root somewhere, or some possible solutions that we can discard along the way. All right, when is a fraction equal to 0?
The denominator and stuff.
When the numerator is 0 and the denominator is not. Everybody's okay there? Okay, so I'm going to take my numerator now and isolate one of the two variables. Should I isolate x or y?
What are you trying to find again?
We're trying to find the points in the first quadrant where that function y cubed plus x cubed equals 6xy has a tangent line with a horizontal slope.
Does it not matter? You just after you get the first one, you got to plug it into the second one.
Well, I think that one way is way harder than the other. I would get the y by itself. Why would I want to do that? I don't want any part of that square root, right? Everybody's okay with that? That's much nicer. Now what do I do with this? I plug it into the original function, yeah. Is everybody okay there? That was the original function. I just plugged that value for y back in.
In this context, what does dy over dx mean again?
The derivative.
No, I know, but like, is it for like a trigonometric? Is it like a rate of change of like an angle or something?
Well, we don't know what the elliptical curve looks like because we didn't graph it, but it's the slope of the tangent line of that elliptical curve at some xy.
Yeah.
So it's like the rate of change of x over y. So I plugged that in. What kind of function did I get here? Polynomial. And how do I solve a polynomial? First step should be set it equal to 0. So let's subtract 3x cubed from both sides. Sound good there? Yeah. Now what?
no, times by 8. No. Can you add to the other side times it by 8?
We can multiply both sides by 8, sure. You want to do that? That's fine.
Just gets rid of that then.
Gets rid of the fraction, sure. Now what?
Factor out x cubed.
Okay, I like that.
Was there another way to do it without?
This is the best. I think this is a good way. Okay, now what? Okay, zero product property, so I can set each piece equal to 0. So here I get x equals 0. What can I do with that?
So the derivative. No, when x is 0, derivative is 0.
It's not
Uh-oh.
possible.
Not a possible solution. We can discard that. And here you said this is going to be the cube root of 16. Do I need a plus or minus on that? No, why not, Frankie? Well, that's true. It's an odd root, though. Odd roots don't get plus or minuses, right? Okay. Let's simplify that a little bit to see if we make that any nicer.
8, 2, 2.
Cube root of 8, 2 root 2?
2
Right,
cube
I'm
root.
just pulling that out.
Well, it can go out to 8 and 2, and 4 and 2, and then 2 and 2, so there's definitely
I
something.
thought it was.
Let's do that. Is that okay? 2 cube root 2 is fine, but we still got to get a y out of this.
Wait,
Well, so we need a point, right?
is 2 cube root 2 not a point?
Well, x is only one part of a point. You also need a y coordinate, right?
I thought we just. Oh no, we didn't.
So I'm going to plug that back into here.
Oh. He's got it. You see what I did there? 8 divided by 3.
Good afternoon, Notre Dame. Let's pause and end this day together. In what moment today did I feel God's peace around me? Dear Lord, thank you for providing me the opportunity to reflect on and recognize moments where your perfect peace was present, whether I noticed it at that time
I
or
want
not.
like 2 minutes after she's done.
Have a great day, Notre Dame. God
2
bless.
minutes.
Teachers, you may dismiss as you are ready.
I have one question for you before you go. How many solutions does this polynomial have? 3. How many did we find?
2.
1. Where are the other 2 at? Should I be looking for those still? Do I need to worry about that?
Oh no, there's the other quadrant.
They're imaginary is correct. Why, Mark? Yeah, why?
Why?
Oh, because if you, that formula. You get the square root of a negative number.
So the solutions from this piece of a difference of 2 cubes, always imaginary. Right? So if a sum or difference of cubes, that quadratic piece, the solutions are always imaginary. That's why we don't have to worry about searching for more. We're done. You're right. I'm not sure it was the right reason, but you were for sure on it right away that they were imaginary, which is great. So I won't be here on Friday. What you're going to do on Friday is you're going to work on this sheet. Do you have to start it before Friday? No. But I'm going to give it to you now so the sub doesn't have to worry about it.
Thank you.
You have to take one?
You should grab one on the way out. Yep.
Thank you so much.
You're welcome. Have a good day, guys. You're welcome. Woo. Now, word of warning on this. This is a escalating difficulty worksheet. So make sure you read the directions in terms of how hard it should be.
Look at the last one.
So the last page, there's some doozies on there.
I can see that.
It should, it's gonna get progressively difficult. Oh, you won't have enough room to write on. absolutely, you can do it in a notebook, that's fine.
Is there any way I can see what I got?
I changed 3 quotients and 2 products. What's up?
Maybe more.